wanted to discuss how we measure mass and weight. And to do that, I'm going to use these standard masses and these three scales that I've got here. The bottom line is whether we're measuring mass or weight, in reality on Earth, we're always measuring weight. The scales are always measuring how hard the Earth is pulling these objects. Because mass and weight are directly proportional on Earth, the force of gravity equals the mass times 9.8. You just have to change the numbers on the dial, whether you're going for mass or whether you're going for weight. So we'll look at these scales and we'll see that. The postal type scale, its dial is in pounds and ounces, and those are measures of weight. But you can see I've put conversion factors on there to turn them into mass. You just multiply by a number. That's even more obvious on the small spring scale. It's got grams and newtons. Grams is mass, newtons is weight. And you can see that there's just two different rulers, and you just read what the needle's pointing at for that scale. This last one is an old scale. It's got two weight units, newtons and dynes. Dynes is an obsolete unit that we don't use anymore, but this is a really good scale, so that's why it's here. I'm going to hang it up, and it will represent how one of our types of scales work. So I've got it hanging on the ring stand, and I'm going to hang this standard kilogram mass from it. And you can see it reads 10 newtons. That's because 1 kilogram times 9.8 is about 10. So how does it work? Well, I think the easiest way to see that is going to be to look inside this spring scale. There's literally a spring, and the more you pull on it, the more it pulls back on you. So it's actually not measuring the weight, it's measuring how much this spring is stretched. So what does that have to do with weight? Well, here's my spring scale, and clearly we're interested in how much the Earth is pulling on that kilogram. So we're interested in the force of gravity. But that kilogram, it's not falling down. And if this was the only force on it, it would be. So there must be some other force acting. And that force is an upward force. And the reason the kilogram's not moving is because these forces are balanced. We could call this a spring force, but it's actually also a tension force. What's literally happening is in that spring, in this scale, atoms are being pulled apart, but they have such strong chemical bonds because of their electrons that they're resisting it. And it's deforming the spring and stretching the spring out, but the spring can take it. And the two forces are balanced, and that's why it's not falling. If I pulled harder on this, the spring would stretch more and the needle would go up. So what this is actually doing is measuring how much its spring is stretched. And as long as there's no other forces acting, that's a good representation of the weight. How does the postal scale work? Kind of similarly, I'll put a standard mass on. Notice it's registering a little less than, well, around 2¼ pounds. A kilogram is 2.2 pounds. Kind of the same deal. We have the weight of the kilogram, and now there's an upward force balancing it out. So this gets a special name. It's called a normal force. And what's causing it is actually that the electrons in my kilogram can't occupy the same space as the electrons on the scale. They're actually repelling each other. It's an electric force that's preventing that kilogram from falling through the scale. So it's actually chemically really different than the other one, but physically it's kind of similar. The scale's not measuring the weight directly, it's measuring how hard it's having to push back. And that's how we get both weight and mass.